Dear students, I welcome you for the today's lecture related to the general heat conduction equation. So basically we need to understand what is conduction, the direct transfer of thermal energy that occurs when the molecules bump into one another, when two substances are touching or they are in contact with each other, then the fast moving molecules bumps into the slower moving molecules. It transfers the energy from molecule to molecule, and that is actually the movement of the energy. The kinetic energy is transferred from one molecule to the another, and as a result the temperature that increases. The transfer of energy from more energetic particles of a substance to the adjacent less energetic ones as a result of interaction between the two particles. So our general heat conduction equation Q, which is equal to Ka dt upon dx, that is what the rate of heat conduction units W, which is equal to K, the thermal conductivity, watt per meter Kelvin, A, area meter square, temperature difference degrees Celsius or Kelvin, and the thickness is in meters. So this is nothing but our Fourier law of heat conduction that is there. Now today we are going to apply this Fourier law of heat conduction and apply it to a control volume system. So our heat rate, which is having the units of watt, here it is written as small q. In this equation it is written as the capital Q dash. So you can write any notation that depends on the book, no issue. But what is there? Q, which is equal to minus Ka dt upon dx, then it will have the units of watt. If Q upon A, that is nothing but watts per meter square Q double dash, that is a heat flux. You have to understand the units and what is there equals to, which is equal to minus Ka dt upon dx. So applying this to the general three-dimensional body, that is the fundamental equation of heat conduction. So we can write the heat flux components in the x, y and z direction by using the Fourier law. So Qx, it is having the units of watt per meter square. This small qx, it is nothing but the heat flux in the x direction. So we are taking the thermal conductivity in the x direction, temperature difference delta T, and differential in the x direction. So changing this heat flux component and relating it in the x direction, relating it in the y direction, and relating it in the z direction. So it is clear from these equations that if the temperature field for the given material or medium is known or can be determined, then the temperature gradient in any direction can be computed. Temperature gradient in any direction that can be computed, either x, y and z direction. You can calculate these values. If the temperature gradient are known, the heat flux or the rate of heat flow per unit area can be evaluated. So heat flux, this can be evaluated, heat flux, or if the area is known, then you can also calculate the Q, heat. The temperature distribution in any material or the medium is usually computed by solving a differential equation of heat conduction subject to the boundary conditions of the problem. So this is what we are going to analyze now. That is, the temperature distribution in any material or medium is usually computed by solving the differential equation in by considering the different terms and different conditions, that is, and applying the boundary conditions for that particular situation. One has to solve that and calculate the values of the heat flux or the heat rate of the heat flow that can be calculated. So basic equation of heat conduction in different coordinate system are derived, that we are going to discuss it. So generally the volume element that is to be considered. Here the volume element, three-dimensional volume element that is to be considered. X direction, Y direction and the Z direction component. Qx is the heat entering in the X direction. Qx plus dx, heat leaving in the X direction with a differential of distance dx. It's a small volume element having the dimension dx, dy and dz. So we are considering this small differential volume element with the dx, dy and dz as the volume elements. The x direction heat that is coming the Qx, y direction heat that is coming as the Qy, and the z direction heat that is coming as the Qz. So similarly the heat leaving from this volume element, that is Qx plus dx, Qy plus dy in the y direction and Qz plus dz in the z direction. Here the units for Q is watts. So applying the basic equation in a Cartesian coordinate, that is the input minus output, which is equal to generation or consumption and accumulation. This is our basic general equation, input minus output, which is equal to generation or consumption plus the accumulation that will be there. So the net heat conducted into the element per unit time, net heat conducted into the element plus the internal heat generation. This is what the input, net heat conducted into the element. That means it's an input plus the heat generation, heat generated per unit time, that will be equals to the heat internal energy, increase in the internal energy per unit time plus the work done by that element per unit time. Here we are not considering there is any work done. So this term that will become 0. So only the three terms that will be remaining. When it's a net heat conducted into the element, that means input minus output plus the generation, or you can say the consumption also. Sometimes there can be the consumption, either generation or consumption that can be there. And third is the increase in the internal energy. That is what? The accumulation term or the unsteady term that will appear in this unit. That is the change in the internal energy or the accumulation term that will be there. So one by one we will consider the each term. It's flow work done by the solid due to the temperature change is negligible. So the fourth term of work done that we are going to neglect. So the terms 1, 2 and 3 of the equation that has to be evaluated. First term we will now evaluate. Let the Qx is the small qx is the heat flux in the x direction at x and phase, that is ABCD. This is nothing but your A, B, C, D phase. Is through this phase the heat that is flowing into the x direction. So the heat flux into the area, heat flux having the units of watt per meter square multiplied by this area dy into the dz. When the area that is heat that is moving in the x direction, that means the area is dy and dz. Then and only this is flowing through the qx. x डायरेक्शन में जो भी हीट ट्रांसफर हो रही है that is crossing the area y and z. x डायरेक्शन से क्रॉस हो रहा है तो एरिया आएगा आपका y and z. So this is the q, capital Qx, that is nothing but the watts, which is equal to minus kx dt upon dx into dy into the dz. So change in temperature gradient in the x direction. dt by dx is a change in temperature in the x direction. That means here the temperature can be something different. At this point the temperature can be different. At the next point temperature can be different. I am talking only in the x direction. So there can be the change in temperature with respect to the distance in the x direction. So Kx is your thermal conductivity of the material in the x direction and dt upon dx is a temperature gradient in the x direction. So the rate of heat flow out of the element in the x direction, out of the element in the x direction. So that will be the qx plus dx, which is equal to the qx into delta by delta x of dx. Qx and the differential d by dx of qx in the x direction. So this will be qx plus, here it is required as the plus, so which is equal to kx, that we have already defined this qx, which is equal to minus kx dt upon dx into dy into the dz. So it is as it is written as qx, capital Qx, plus d by dx of qx. So d by dx of qx is this term. The same this term is appearing here also, and we are differentiating with respect to the d by dx. So this is what? D by dx of qx. D by dx of qx. This dy by dx that will be there. So this plus this that will be there, right? So this is what the qx is. So differential in the x direction. Now the net rate of heat entering the volume element in the x direction is the difference between the entering and the leaving. So difference between the entering and the leaving. So Qx and Qx plus dx. So Qx we have already calculated here, and Qx plus dx, that is calculated from here. So the net heat, that is nothing but Qx minus Q of x plus dx. So you will get this thing, or you can say this thing, and this is nothing but the Qx. Here it requires. So similarly, you can have the net heat flow in the y direction. I can write Qy here, which is equal to minus Ky dt by dy into the dx into the dz when I am writing for Qy. So similarly here, my y term and the subsequently the z term that will appear. So now combining all these three terms, that is x, y and z direction, the total force term, that is what the net heat conducted into the element dx, dy, dz per unit time, that will be the summation of all these terms. Net heat term in all the three directions. This is for single direction. This is for y direction, this is for z direction. So total net heat conducted into the element. This is, you can collect d by dx of this term, and this term, that can be collected and multiplied by dx, dy and dz, which is taken as the common. So this is the net heat conducted into the element. Then the second term is related to the internal heat generation or the consumption per unit time per unit volume. That is what? The watts per meter cube. Q dash is having the units of watt per meter cube, because we are defining this as the internal heat generation per unit time per unit volume. First term का unit क्या है? Qx is having the units of W, watt. So here second term units I have to manipulate as the watts only. But the Q dash is nothing but the internal heat generation per unit time per unit volume. Per unit time, that is joules per second heat generation. So that is why Q dash into the dx, dy and dz, we have multiplied it by the volume meter cube. So units will be the watt only here. Now the calculation of the third term, that is the accumulation term or the change in the internal energy of the element over a period of time dt. Change in the internal energy for the element over the period of time dt. That is what? Mass of the element m into the specific heat Cp into the change in the temperature of the element in the time dt. Change in the internal energy. Internal energy may change you are taking into account. So change, when we talk change in internal energy, that is related to the mcp delta t. इंटरनल एनर्जी, कितनी कैपेसिटी, कितनी एनर्जी है किसी मटेरियल में, दैट इज टॉक और कैलकुलेटेड फ्रॉम द एमसीपी डेल्टा टी. When it's a mcp delta t, that is what we are writing m mass in terms of volume and density, Cp, and the temperature dt. dt is the change. Now the units of this, that will be the only joules. So we are dividing it by the time to make the units of watts. So rho Cp into dt upon dt, rho Cp into dt upon dt into the dx dy dz. That is what? The change in the internal energy per unit time. It's a per unit time. Here we have calculated the change in the internal energy. Here it becomes the change in the internal energy per unit time to make the units of watts. So all the three will have the units of watt. So now all the three, they are to be written in a single equation, where we have deleted or cancelled the terms dx, dy and dz, that is the common in all the three equations. So these three equations are there. First term, that is the net heat conducted into the element. The second term, Q dash, the internal heat generation per unit time, internal heat generation. The third, the change in the internal energy per unit time. So these three terms, out of that we have cancelled this dx, dy and dz, dx, dy, dz, and here dx, dy, dz, and multiplied by the K thermal conductivity. K is here. So K, that is there, Kx, Ky and Kz, that is there. Since the most engineering problem, the material that is same, or you can say that is the isotropic, that means the thermal conductivities in all the three directions is taken as the constant K. So I can neglect this Kx, Ky and Kz and write them as the K, and here I have manipulated or adjusted this K, and here also adjusted this K divided by this K divided by this K. Now the term rho Cp upon K, that is nothing but the alpha. Alpha is the thermal diffusivity term, which is equal to K upon rho Cp. Thermal diffusivity is K upon rho Cp. So K upon rho Cp is known as the thermal diffusivity, and it tells about how fast the heat is propagated or diffused through the material during the change of temperature within the specific time. The diffuse through the material, how the temperature or the heat propagates into the material, how the temperature diffuses into the material during the change of temperature with time. टेम्परेचर तो चेंज हो रहा है मेरा, कब? टाइम के साथ टेम्परेचर हो चेंज हो रहा है. दैट इज व्हाट वी राइट dt upon dt. Now coming to this is the general three-dimensional heat conduction equation. This is the general three-dimensional heat conduction equation. That is, here the two variables are there, that is temperature, that is getting varied with the distance, and the time and the distance, that is there. Temperature is getting varied with the time and the distance. Now these three terms, that is called a diffusion term. that is delta square T upon delta x square plus delta square T upon delta y square plus delta square T upon delta z square. This is a general diffusion term. Q upon K, that is the heat generation. Q dash is what? The heat generation. And the third term, that is the dt upon dt, is the unsteady state. Unsteady state, the temperature is not constant. Temperature is varying with respect to the time. It is what? Continuously changing the temperature. That is what we are saying, that it's an unsteady state. Variation of anything with respect to time, whether it's a temperature, whether it's a concentration, whether it's a pressure, that becomes your unsteady state. If you will think of energy balance, mass balance, or momentum balance equation, this unsteady state will exist. In case of energy balance equation, it's a temperature that is getting varied with the time, dt upon dt. In case of a concentration or the material balance equation, it's a change in concentration, that is dc upon dt, change in concentration with respect to time. Capital T is the temperature, small t is the time. You have to remember that capital T is the temperature and small t is the time. This is the unsteady state condition. So now the three terms that is there: diffusion term, generation term, and the unsteady state term. Now out of this, I will consider that if it is a steady state term, so this term will go as the 0. My remaining equation will be only this one. That is one condition. Then second condition is the generation term, that will be 0. There is no heat generation or heat consumption. That can also happen. The heat that is coming in, that is going out, that can only be there. This is the second condition. So one by one, and there is a stage where neither there is generation nor there is a change in temperature. So both the conditions are there, that is no generation and unsteady state condition that is there. That is, we will see one by one. That is, uniform thermal conductivity is there. This is what all our three terms are there: the diffusion term, the generation term, and the unsteady state condition term. So I can write this term in terms of a Laplace transform. This is nothing but delta square t. The Laplace operator of the t is written as this term, delta square t upon delta x square plus delta square t upon delta y square plus delta square t upon delta z square. So in terms of a Laplace transform, my general heat transfer equation, that can be written like this: delta square t plus q upon k plus 1 upon alpha delta t upon delta t. So this is the diffusion term that reduces in terms of a Laplace transform. The heat generation term is there and the unsteady state term is also there. This is the Laplace equation, that is called as the Laplace equation. This equation is called the Laplace equation. Then the second is the steady state condition. Steady state condition, the temperature at any point in the material does not change with the time. Temperature at any point in the material does not change with the time. So your change in temperature dt, d capital T upon d small t, which is equal to the 0. So your general heat conduction equation becomes this, the last term that goes to the 0. So this is called the Poisson's equation. When it's a steady state condition, my delta t upon delta t term becomes 0. the remaining two terms, that is the diffusion term and the generation term, exists. So this is called a Poisson's equation. That is one condition. Then no heat source. No heat source. So Q dot term, that becomes equals to the 0. So the remaining term are the diffusion term and the unsteady state term. That is the diffusion equation. This diffusion equation, that is called the Fourier equation. This diffusion equation, that is also called the Fourier equation. So one is the Laplace equation. The next is the Poisson's equation. And third one is the Fourier equation. So this different equations, that depends on whether the heat is generated or whether it's an unsteady state or whether there is no diffusion term. So in addition, the process is the steady state, then the heat conduction equation becomes delta square T. That is what the Laplace equation that is called. Now coming to the one-dimensional heat conduction equation. So this is the three-dimensional equation that we have already discussed. Out of that, only one-dimensional equation we have to consider. So only delta square T upon delta x square, that will be remaining. Rest of the terms, that will go to 0. If the temperature varies only in the x direction, then your Laplace operator takes the form delta square T upon delta x square. So this will become, and for steady state case with no heat generation, that is also the condition, one dimensional heat conduction equation with no heat generation and the system is steady state, then your equation becomes delta square T upon delta x square, which is equal to 0. So understanding this equation is essential. ये equation कब आ रहा है? Only in one direction for steady state and there is no heat generation. Means three conditions are there: one dimensional, steady state and no heat generation. तो उसका reduced form मेरे को मिल रहा है जनरल हीट कंडक्शन इक्वेशन का, डेल्टा स्क्वायर टी अपॉन डेल्टा एक्स स्क्वायर विच इज इक्वल टू 0. एंड most of the problems we are going to apply or use this equation. Now one by one we are going to add the terms as the unsteady state and the case of a heat generation term. Then our equation will going to add individual terms. So this is the general heat conduction equation. Is very much essential to understand what are the different and the basic terms that are involved. The diffusion term, the generation term and the unsteady state term. ये जब इक्वेशन आपको समझ में आ गया, so that you can apply the different conditions to your system. When there is one dimensional, all these three things, all the things will go to the 0. Only one direction, no heat generation and unsteady state condition. Then if it is a one dimensional with no heat generation, so one dimensional and unsteady state condition equation. Similarly, I can have the one dimensional equation with the heat generation. That is what the permutations and combinations of these general three-dimensional heat conduction equation is to be done. Now this is in x, y and z coordinate system. That is why it is called as the Cartesian coordinate system. Now we will consider the heat conduction equation in cylindrical coordinate system. So in case of your cylindrical coordinate system, it's r, theta and z direction that is to be considered, so that I can write the equation in the x, y, r, z and phi, that is qr, which is equal to minus k dt upon dr into r d phi into the dz. So net heat entering into the system is what? qr minus qr plus dr. So the same way I have to consider the first term of the net heat conducted into the element in dr, r d phi and dz per unit time. Then the second term of the internal heat generation, that is q dot r dr into d phi into dz, and the third term, the change in the internal energy, that is what the accumulation term, change हो रही है internal energy. Internal energy is talked in terms of a temperature. So when I am talking in terms of a temperature, then the change in the internal energy is nothing but dt upon dt, d capital T upon dt. That is what the change in the internal energy that will exist. So I am going to collect 1, 2 and 3 terms and write it in the generalized cylindrical coordinate system. So my general three-dimensional equation in cylindrical coordinate system will become this. Here you have to only remember this general three-dimensional equation in cylindrical coordinate system and in okay, this is what the final form of the general heat conduction equation in cylindrical coordinate system. Here also I can reduce this term to the no heat generation, unsteady state condition, only in one direction condition that can be manipulated. Then the heat conduction equation in spherical coordinate system, that is x will become equals to r sin psi cos phi, y r sin psi sin theta and z r cos psi. So my general three-dimensional equation in cylindrical coordinate system, that becomes equals to this. I have to remember cylindrical coordinate system, spherical coordinate system and Cartesian coordinate system. The diffusion term, the generation term and the unsteady state term. All these three terms, they are to be remembered. Then I can have the permutation and combination of the different equations, so that I can get the Laplace equation, I can get the Fourier equation, I can get the Poisson's equation.